Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Harun Rizam, and today I will talk about our assignment 1 on life expectancy data set. For introduction, this assignment presents a life expectancy data analysis using various machine learning techniques to predict life expectancy based on demographic, socioeconomy, and health-related indicators. The dataset contains information collected from different countries over multiple years, encompassing various factors that may influence life expectancy. Our primary objective of this analysis is to explore the dataset in identifying significant features and reveal the performance of different machine learning models in predicting life expectancy. This experiment is significant as it delves into understanding the determinant of life expectancy and evaluating the efficacy of machine learning technique for predictive modeling. For the first, basic feature selecting using traditional regression model. Second, feature selection using lasso regression. And third, feature selection technique using principal component analysis. And finally, we present a comprehensive analysis of the result and compare the performance of different techniques, highlighting the strength and limitation in predicting the expectancy. And overall, the research aims to provide valuable insight into public health trend and inform evidence-based decision-making in healthcare policy and resource allocation.
Assalamualaikum warahmatullahi wabarakatuh. So I will be explaining the dataset part, why we choose the dataset. And okay, as you can see, here is our dataset overview. So you can get this dataset from the QR code that I attached here. So this is the column name and this is the description. We have country, we have year, we have status, and so on. So next we look into the shape of the dataset. So it have an estimate of 3000 entries and with 22 columns. So we can see that this dataset have a high dimensionality. So why we need a high dimensional data? Because when we do the feature extraction, we want to make sure that the column we have enough for the fitting our models. So we want to make sure that the data set that we choose is 20 column and more. Next, we will look into the summary statistic of the data set. So you see we have count, mean, standard deviation, mean, quantiles, and max. So at first we can see the count. Count for each column are different. So this count, if it is different, it means that the column have null values. So these null values that we need to eradicate. So the count values will be the same. So we want the mean values to be not close to 0 because we don't want the values to center around 0. So it is not good for analysis. And also for standard deviation and variance, we want it not to equal to 0. Like if it is equal to 0, it suggests that the column does not have any variability or spread, making it very uninformative and very hard for analysis. And we also look into the min and max. Like if let's say min and max are the same values, it means that all the values in that column are identical. So we don't want that. If let's say some of the column have like go against these rules, so we need to drop the column. So next we go to the data types. As you can see, we have object, integer, float. We have numerical values, but we also have objects. We have float, we have integer, but we have objects. So these objects we need to convert it into numerical values by using labeling coding. So it makes it us easier to fit our model.
So now I will explain how this flowchart works. So this flowchart shows the steps involved in analyzing our datasets, which is life expectancy datasets. So it covers like data pre-processing, EDA, model evaluation, and comparison to predict. So now, first we have upload the dataset, which is to load the dataset, the CSV file into the Google Colab. After that, we will perform the EDA analysis to understand the structure and variables or the patterns in our datasets. So now, to perform the EDA, we do handling nulls value. We identify and address any missing values in the dataset. After that, we perform label encoder to encode the variable into numerical format. So we can prepare the data for the machine learning algorithm. So normalizing numeric features is we scale the numerical features to prevent bias in the model training. And making dataset copies, we create copies of the dataset to facilitate the different analysis and prevent the overwriting data during pre-processing. So after we all do these steps, we will go for plotting seaborne and heat map. And after that, we do model evaluation, which means we evaluate the model, the baseline of performance of KNN and linear regression models on the original dataset. So when we run the KNN and linear regression, so we have basically we have three models here. First is we do a basic features selection, and second we do lasso regressor, which is a wrapper technique, wrapper feature selection technique, and third we do perform PCA, which means principal component analysis. So for the basic feature selection, we use like dropping highly correlated technique or drop irrelevant columns. For the lasso regressor, we use the technique to select relevant features by penalizing non-zero coefficient and dropping irrelevant features. For PCA, we apply PCA for dimensionality reduction to reduce the number of features. After that, after all three methods have been performed, we analyze it with graph. We compare the performance of models before and after feature selection and the techniques. So after that, we drawing the conclusion based on the graph, based on the analysis that we have. So that's for flowchart explanation.
Okay, now I will be presenting about our machine learning model. So in this particular assignment for this experiment, we use two machine learning models, which are first one is KNN regression model and the second one is linear regression model. So why we chose KNN as our machine learning model? It is because KNN is intuitive and easy to understand. KNN is a simple algorithm that relies on the similarity of data points in the future space. KNN also doesn't make assumptions about the underlying data distribution, making it versatile and applicable to various types of datasets. KNN also can handle both numerical and categorical, making it suitable for a wide range of datasets. And last one, KNN can capture nonlinear relationships between features and the target variable by considering the nearest number. Next is linear regression. The reasons we chose linear regression as one of our machine learning model, it is because linear regression provides coefficients for each feature, allowing for easy interpretation of the relationship between predictors and the target variable. Linear regression is computational efficient and can handle large datasets with many features. Linear regression also is a well-established and wide-used statistical method, making it a common choice for benchmarking and comparison with other models. Linear regressions assumes a linear relationships between predictors and the target variable, which can provide insight into the underlying data structure in our dataset. Next is basic feature selection. So we can see here that this is a seaborne pie plot, seaborne pepper, and this is a heat map. So these two graphs purposes is we want to identify the relationship between those columns in our dataset. So the columns that provide a highly correlated dataset. In this heat map, for example, they will display as a red one. So whichever columns provide a red one color, that means they are highly correlated and we can drop them. So in basic feature selection, we drop a few highly correlated columns. In other words, the relationship between several particular columns produces a large correlation that leads to nearly redundant data. So where the code for dropping the high correlated column is we have to do it manually, and after that we have identified these four columns under 5 deaths, thinness 1 until 19 years, income composition of resources, and GDP. So we drop these four particular columns in our dataset. Seaborne, Pepplot, and heatmap are two methods we use to spot the highly correlated columns. The reason for this method is we want to ensure that our result will be more efficient and understandable. Furthermore, highly correlated features can lead to overfitting, so we do not want that, where the model learns to fit the noise in training data rather than the underlying patterns.
So uh, now I will explain how the code works. So first, we assign the features value to x and the target value for y. And now we train them. We use test size, which is 0.2, which is 20% of the data will be the test set, and the remaining will be 80%. So after that, we scaling and centering the data. Um, is a common pre-processing steps in any machine learning workflow. It helps standardize the range of features, make it more fair when to penalize the features. So after that, this code is the lasso regression code. This code is how we implement the lasso regression, followed by the evaluation of the R squared and MSE. So first as you can see here, first we initialize the lasso regression model. We are using max iteration 10,000, which is the default parameter. Max iteration 10,000 means the maximum number of iteration for the optimization algorithm to converge. So we train them, we fit the model. Now we do a prediction. We do the model prediction and we calculate the R square and the MSA. So this is the value of the model. So this is the code for the plot, which can help us understanding how the coefficient of different features shrink towards zero because we are using lasso regression. So this graph right here demonstrates the effect of regularization on feature selection and can be used for understanding which features are deemed important by the model under different level of regularization. So this is the graph that shows the correlation between various values and the alpha values, the alpha.
Thank you. Next, for features extraction technique, we use PCA because it addresses the challenges of high-dimensional dataset by distilling complex information into a more manageable form. As dataset become increasingly high-dimensional, computational limitation can hinder the recognition of meaningful pattern. PCA overcome this by transforming the dataset into a lower-dimensional representation while preserving essential information. By removing irrelevant or redundant feature, PCA allows model to focus on the most informative aspect of data, resulting in better accuracy and reduced overfitting. First step is the identifies intrinsic dimension. Determining the intrinsic dimensionality in principal component analysis is crucial for effective dimensionality reduction while preserving the essential structure and variability of a dataset. In involve, it involves identifying the optimal number of principal components needed to capture most of the data variance. The provide code snippet showcases the construction of a machine learning pipeline for scaling, performing principal component analysis, and visualizing the explained variance of the principal component. To begin, a standard scalar object is created to standardize the feature of the dataset, ensuring they have a mean of 0 and standard deviation of 1. Next, an instance of PCA is instantiated without specifying the number of components, providing flexibility in the analysis. The pipeline is assembled using make pipeline function from scikit-learn library. This pipeline applies the scalar and PCA to the data in a sequential manner. It learns from the data by fitting the pipeline to the dataset df-copy2, allowing the scalar and PCA to adapt the dataset characteristic. Finally, a bar chart is plotted to visualize the explained variance of the principal component. This visualization provides insight into the amount of variance captured by each component. It helps in determining the intrinsic dimensionality of the dataset and identifying the principal component that contribute most significantly to dataset variability. Next, the following code snippet demonstrate the application of PCA to a dataset highlighting the pre-processing step of scaling and centering data. Once the dataset is standardized, a PCA model is created with a specified number of components which we have seen before. In this case, we set it to 5. The model is then fed to a standardized dataset calculating the principal component and determining the variance explained by each component. After the fitting process, the original dataset is transformed into new feature space defined by the principal component. This transformation occurs by using the transform method, resulting in a transform dataset called PCA features. This transform dataset effectively captures the essential information of the original data while reducing its dimensionality. Finally, the shape of transform dataset is printed to provide insight into the number of samples and representation dimensionality achieved through the PCA process. The next provide code segment will generate a data frame called PCA_DF that contains the principal component obtained from the PCA transformation. Its principal component is represented as a column in the data frame labeled as PC1, 2, 3, 4, 5, which corresponded to the 5 component extract during the PCA process. This data frame offers a structured representation of the transformed dataset, showcasing the reduced dimensional form achieved through PCA. The PCA data frame, PCA_DF, provide a foundation for further analysis and interpretation. By examining the value in each principal component, we can gain insight into the contribution of different features or dimensions to the overall variance. This aids in understanding the relative importance and impact of each component in shaping the dataset structure. Next, for the core of model evaluation, the dataset derived from PCA, PCA_DF, and corresponding target variable that expectancy are derived into training and testing set using the train test split function for scikit-learn. The purpose of this division is to assess the performance of regression model in prediction type expectancy based on principal component obtained through PCA. The training set, X train, Y train, consists of 80% of data, while remaining 20% form the testing set X test, Y test. This split allows us to train the model on portion of the data and evaluate the performance on unseen data. Two regression models are trained and evaluated using the training and testing set. First, a k-nearest neighbor (KNN) regression model with 5 neighbors instantiated and trained on training data. Predictions are made on the testing using X-test and performance metrics such as mean square error and R-squared score, calculated using the predicted value I predict, Y predict, KNN, and true label Y test. Next, a linear regression model is trained on the same training set and evaluated using testing set. The MSE and R-squared score are computed to assess the performance of the linear regression model in predicting life expectancy. To organize the present and evaluating result of both the model, a data frame result4 is created. This data frame provides a clear comparison of the MSE and R-squared method for the KNN regression and linear regression model. It helps to evaluate and understand the performance of each model in predicting life expectancy based on the principal component derived from PCA.
Regressions. From here, you can see that KNN regression recorded much lower mean squared error compared to linear regressions. So lower mean squared error means much lower the model to make an error. Hence, it have a higher accuracy to make predictions. This might be because the dataset itself is non-linear and not suitable for linear regression. So that's all from our group. Thank you.